Yes. So I'm audible, no? Now?
Yeah.
Yeah, okay. Okay, so what I planned today, I will mostly discuss on the Ingham inequality. I don't know, maybe it is familiar to the group, I'm not very sure. So I briefly give the proof also. And then I will just show the, or give some outline how it is important to the control theory, or why that inequality comes into the picture in PD and control theory point of view. Okay, so yeah. Yeah, so first of all, if we start with wave equation, okay, and the question is that we will discuss mostly, so control problem can be viewed as inverse problem in particular. So why it is inverse problem, that I will explain a little later. So mostly we started, today we started the discussion with the wave equation. As you see here, this is utt minus uxx equal to 0. So this is the wave equation, and the domain for the spatial variable x is posed in 0 to 2 pi, and t is running in r. So it could be greater than, mostly t greater than equal to 0. But for now it is t in the whole r. And since for spatial variable x, we have the boundary region or boundary domain, to make the PD well posed, we need first of all the boundary condition. Okay, so here I am taking the Dirichlet boundary condition. That means the value of u at each boundary point, that is x equal to 0 and x equal to pi, at both point the value of u is equal to 0. So this is homogeneous Dirichlet boundary value problem. And then since it is a time dependent problem and second order PD in particular in time, so we need to pose the initial condition also. So that is given here. So u naught, basically the value of u, which is posed or given at t equal to 0. And since it is second order in u, so you need another condition in initial condition. So that's what we pose the initial data at the value t equal to 0 for ut. Ut is the t derivative of the function u, and that is equal to u1. Okay, so this is the formulation of the PD. So this PD in particular model or describes the vibration of a string. You can consider a very thin string which behaves like one dimension in space variable, or the length is only, there is no weight, only the length is considered, and the two end points of that string is fixed. Okay, so both endpoints are fixed, and for that string we can consider this model or this wave equation just now what I prescribed. Okay, so now if you remember that the very fast PD course, you have many trick or method how to solve this wave equation. Okay, because this is a simple one dimension wave equation. So one way to do is using separation of variables. Okay, and using the separation of variables, you need that Fourier series expansion, and that is precisely coming as a eigenfunction of that uxx, which is posed in that 0 pi boundary condition with the Dirichlet boundary. Okay, so that's what you will get, that the expression or expansion of the value u in terms of that Fourier series, which is given here. Okay, so uxt is equal to summation of ak cos kt plus bk sin kt, and so this is the function of t, this what that coefficient I just read, and then it is multiplied with sin kx, and k is running from 1 to infinity. So note that since we have this directly boundary condition, so that's what I need that sin k function, because you could ask why don't we expand it with cos function, right? That also we could do provided we have Neumann boundary condition. But here I have to choose the solution such that this boundary condition holds. So that's what I have to take the sin kx. Okay. So this is the Fourier series expansion we have for the solution. So now there are two ways. Okay, so the direct problem, generally what we solve in PD class or PD course, that u0 and u1, the initial conditions are given. Then you find out the solution uxt and you do energy estimate or whatever is required. Okay. But now we are asking the inverse problem. The question is in the reverse way. Now the question is that suppose you know that uxt, that expression is given, and in particular if we go to the next page, yeah, in particular what I know that the first derivative of u with respect to x variable, okay, at the point x equal to 0, that is the one boundary, left boundary, that value ux, that the value of ux at x equal to 0 for all t belongs to 0 to capital T is given. Okay, the some estimate or some measurement of the solution at the boundary of the domain is given. So now the question is that can you retrieve or can you get back the initial condition? Okay, or can you determine the initial condition which was posed at t equal to 0 in terms of or using the measurement was what is given to you. Okay, so that is we call in PD or control theory, that is basically the observability problem. So that means in the boundary some quantity of u, it could be the vibration or the displacement or the some energy of the solution. Here in this case that normal derivative of displacement u at x equal to 0 in that left hand side or the left hand boundary is given. Okay, so that observation is known to you. So your problem is that you have to find out or you have to determine the initial condition u0 and u1 from that information what is already prescribed. Okay, so it is not always doable or it's not trivial, right? So we know that direct problem that well-posedness of the PD and etc. can give the solution when the initial condition is prescribed. But when the observation is given, there is no guarantee that that observation is enough to solve this inverse problem. Okay, in general. So that is one part of the research topics in control theory, that which observation is enough and etc. Okay, but let us see in that simple case what happened. Okay, so now you know that ux at left boundary, it is given. Okay, but and we have to find out or some estimate or some information for the initial condition u0 and u1 from that observation what is given. Okay, so first of all which space we should consider. Okay, so since we know the well-posedness of the wave equation, so it is standard that we consider or we would like to consider the initial condition u0 u1 from the space h1 0 0 pi cross L2 0 pi. So h1 0 0 pi, this is a Sobolev space. So that definition is just given below. So it means that is collection of the functions f such that f is L2 function in 0 pi. Then its weak derivative exists, and that is also a function of a function in, or that is also in L2 0 pi. And not only that, the trace of that function f at both boundary x equal to 0 and pi, it is equal to 0. Okay, so h1 0 is that the collection of such functions f. Okay, okay, so now the question, that inverse problem, what we would like to understand, that the question is that if t greater than equal to 2 pi, then whatever that map is given here, that you, so this is the forward problem, that mapping F is going from say U0, U1 to that observation UX. So this is the forward problem. So our question is that this inverse of that mapping exists or not, and whether it satisfies any bound or not. Okay, so that's what given in this bullet, that if t greater than equal to 2 pi, then this map is 1 1 and continuous from H1 0 cross L2 to that L2 0t, that is the space for the observation. And moreover, such estimate holds. Okay, so that is the claim we are doing here. Okay, so here in particular we are telling that a forward system is well posed anywhere or exist. The mapping is 1 1 and continuous, and in particular the inverse is also exist, and the inverse is a continuous mapping, and that will come from this first inequality. Okay, so first inequality will give the boundedness of the inverse mapping, and whereas the right hand inequality will give the boundedness of the forward mapping or direct mapping. Okay, so for this particular case, how do we prove this estimate or even the well postedness? Okay, so that is very simple. So this is a simple application of Parseval identity. Okay, so let us see what we do using Parseval identity. So what I have to do in particular, I know the expression of u, no? Here I know the expression of u. So I have to find out what could be u naught. So if I put t equal to 0, I will get that initial condition u naught. I have to take a t derivative of u and then put t equal to 0. Then I will find out what could be the u1, and I have to estimate that u0 and u1 in that particular Sobolev norm. And then I have to estimate that x derivative of u, putting x equal to 0. So that will be the middle term here. Okay, so I will calculate each terms now one by one, and that is just straightforward application of Parseval identity. Okay, so what we do, that if we just use that that expansion what we have for u, so then we can easily get that ut x0 satisfies this identity, and ux at t equal to 0, it satisfies this identity. Okay, and now if we need to do the estimate, so this ut x0 is basically u1, so I need to estimate the L2 norm of u1, and that is nothing but the summation of k squared bk squared. You will get that pi by 2 as a coefficient. But the L2 norm of U1 square is nothing but in terms of that summation of k squared bk squared. That coefficient is coming. Okay. Now, similarly, I have to estimate that U naught H10 square norm. So I don't know whoever is not familiar. So H10 norm is equivalent to the gradient norm. Okay, and that is due to the famous inequality named by Poincare mathematician. So we call it Poincare inequality. So using that Poincare inequality, you will have the estimate of H10 norm of U0, and that will involve in particular the summation of k squared ak squared. Okay. So all these two estimate I already have now. So here in particular, I use that sine k, that family of functions of sine kx is orthogonal in L2 0 pi. And similarly, cos kx is also forms a orthogonal family in L2 0 pi. Okay. So these two things just we used here. So now next we will estimate that what is that no, that middle term in particular. So that is ux. We take the x derivative and then we put the value x equal to 0, and we it turns out that identity looks like in this particular way. Okay, so now we have to estimate this term for all, L2 estimate of this term for all when t is running from 0 to capital T. So here everything is fine. So that's what we, in particular, if capital T is in that form 2m pi, or you just, for simple case, you imagine T is equal to 2 pi. So then we know that cos kt and sin kt forms an orthogonal set in L2 2 pi, and in particular for L2 2 m pi for any integer m. And using that again, due to Parseval identity, we get this identity holds. Okay, so this once, as soon as we have this and we compare that above two identity we obtained here for u1 and u0, using all those, we ultimately get that required inequality what we are looking for when t is equal to 2m pi, where m is an integer. Okay, so but our claim was that for any t greater than equal to 2 pi, and that can be easily obtained now, noting that capital T, if capital T is greater than equal to 2 pi, then there exists a integer m such that you can bound capital T in this particular way. And then for the lower bound, you apply whatever you obtained already in that interval 0 to 2m pi. And for the upper bound, you use whatever you derived just now for the interval 0 to 2m plus 1 pi. Okay, so just doing this manipulation, ultimately you get this identity which we are looking for. Okay, so this is just use of Parseval identity. I just wanted to show you that when you have that Parseval identity, you can prove the well-postness of the wave equation, of the solution of the wave equation, at least in one dimension easily. And not only that, even that inverse problem also can be solvable. Okay, so this is the good and simple case. Okay, so now suppose I make the things little complicated. I mean, not too much, just little. So I add one lower order term here. Okay, so now it is wave equation with a lower order term plus u is coming here. And then you have the initial condition and Dirichlet boundary condition as earlier. Okay, so then again you will get the similar way, you will get that expansion or the expression of that solution u in terms of that cos, now it is omega kt and sine omega kt, and for x you will get sine kx, so that is fine. Okay, but the problem is that now omega k is not like k, so it's not harmonic now. Okay, so what do you get here now? Omega k is in the form of root over k square plus 1. Okay, and then the problem is that this cos omega kt and sine omega kt is not, no longer orthogonal in any interval 0 to t. And hence, wherever that Parseval identity we used for such basis function or such set of family, we could not use again that. Okay, so we need a generalization or some extension of Parseval identity. Okay, for such type of exponential when omega k it is real, but it has it need not be in that particular form, and in particular that cos omega kt sine omega kt is not orthogonal, then when we can relax that Parseval identity, and which kind of condition is needed for omega k at least obtain some inequality instead of Parseval identity. Okay, so that's what we are looking for now. And that's where that Ingham inequality came to the picture. Okay, so I will start that. Is there any question so far, or is it okay?
Yeah, at least from my side.
Okay, but it's audible, no? I'm that
Yeah.
very.
Yes,
Okay.
yes.
Okay. Okay, so now we go to that Ingham inequality. So that is due to that name of the mathematician is Ingham, and he obtained that result in 1936. So his statement, I mean, the proof is also very simple. So you will see how it goes. But he has how, why that, what is the statement of that theorem. So let us see that first. Okay, so his claim is that if omega k is a family of real numbers, okay, satisfying the uniform gap condition. So say omega k plus 1 minus omega k is greater than equal to some gamma which is strictly greater than 0, and for all k belongs to z, so that consecutive exponents will have this particular gap condition. Okay, and now he is claiming that for any capital T greater than pi by gamma, there exist positive constants C1, C2 depending on that gamma and capital T, such that for all function given by in this particular, so this is the series expansion in terms of this exponents e to the power I omega k t. So he is telling, and provided it is given that xk is in little l2, so the convergence is not an issue. So then his claim is that for any t greater than pi by gamma, this inequality holds. Okay, so you see immediately that, okay, we lose that idea, it's not identity or equality, but we have that inequality, and this could be, one way to generalize that Parseval identity. Okay, so this is his claim, and proof is also not very difficult, so we can easily see the proof, and then we can go to more general case. Okay, so his idea is that, so first, okay, so it was for any capital T greater than pi by gamma, so that condition is important, and yeah, so that interval, or we are taking the L2 norm in L2 minus T to capital T. Okay, so his first observation is that we can reduce the problem for the case T equal to pi and gamma is strictly greater than 1. Okay, and this is not difficult to see, I just, for completeness I just wrote it. So you just do the simple change of variable, since you know that capital T gamma is strictly greater than pi, you do the simple change of variable in this way, and then you go from interval minus t to minus t to t, so that interval you change to minus pi to pi. Okay, and when you do the change of variable, you will get some coefficient thrown out, so that is fine, but your exponential also will change. Okay, so it is also just multiply by capital T by pi. Okay, so I rename it this coefficient, sorry, this exponentials, I renamed it by mu k, so this is equal to now T omega k by pi. Okay, so now if we calculate, or if we want to check the gap condition, so this basically mu k plus 1 minus mu k is equal to now T by pi, that omega k plus 1 minus omega k, and that if you calculate, since we knew at the beginning itself that omega k satisfy that gap condition with gamma, and T is strictly greater than pi by gamma, so ultimately what you get, that here the gap condition denoted by gamma 1, which is precisely capital T gamma by pi, and which is strictly less than strictly greater than 1 due to our assumption. Okay, so that is very crucial afterwards. Okay, so we need in particular that gamma 1 is strictly greater than 1. Okay, so once we agree with these things, so it's easy, I mean, so now it is fine that it is enough for us if we prove the inequality only for the interval minus pi to pi, and where that gap condition gamma 1 is strictly greater than 1. Okay, so now we will concentrate only to prove this inequality in interval minus pi to pi. Okay, so first we will prove that first inequality. So that leftmost inequality, I will call it first inequality. So first we will prove this part, and then the other part will more or less straightforward. Okay, so okay, just to be consistent. So I will use that infinite sum throughout, because I will just give the outline. But the correct way to do, considering the partial sum and then taking the limit goes to infinity at the end. Once you know all the constants are independent of this n and k. Okay. So now, so if we just see what will happen, so one way that is due to Ingham. So his idea is that you suppose consider a continuous function, small g, and consider a Fourier transform of that small g denoted by capital G. So in particular, it is defined in this way. So yeah, there could be some weight 1 by 2 pi, but that he is not considering. So we consider this capital G and small g. Okay, we have to determine that which is the correct small g and capital G we need in our case. But suppose we just blindly go with that. Okay, so what we are willing to do with this small g and capital G. So let us see that. So then first suppose we consider this term. Okay, so if we just do the manipulation and the direct calculation, then ultimately we will get that this right hand side what is written. So that capital G is basically the Fourier transform or whatever is just defined above, and then this product term is coming involving xk and xn bar, and this is a double sum. Okay, over k and n, which is running in which could be any integer. Okay, so now we separate it in these terms. We separate into two cases when k is equal to n. So that is the simple one. So we put g, if mu n equal to mu k, so it is nothing but g0. And then we get the summation of xk square, which we need actually. So we'll keep it, this is a good term for us. Then we have plus, and then the second term is basically that mixed term or the product term between xk and xn bar. Okay, so the idea is that how do you estimate, or what conditions do you need on G so that you can manage the second term in particular. Okay, so the first way to use Cauchy-Schwarz, okay, to handle, and we are looking for the lower bound. Okay, so we keep the first term as it is, then we get use the Cauchy-Schwarz, then we get minus half into summation of this mod x square k square plus xn square, then modulus g mu n minus mu k. Okay, and again it is with double sum. Okay, and now provided you know that capital G is even. So it means that G phi is equal to G minus phi. So using the symmetricity, we hope, I mean, suppose we can get that capital G, such capital G. So then that, these two terms we can combine, and at the end we can write the second term, the two will go. The second term will just look like in this particular way. Okay, so that summation outside it over k, that modulus k square, and now the summation over n, but n is not equal to k, and then you have this capital G, that function evaluated at mu n minus mu k. Okay, so ultimately we have this, suppose we, whatever we are claiming, that is capital G is even function, and it has some nice property. Provided we have all these, then we ultimately get this last line, okay, last inequality. So now it remains to show that whatever that summation here, if it is uniform in k, say some C naught or something, and that C naught suppose is strictly less than G0, so then we can expect some lower bound. Okay, in that from this line. Okay, so that is our next goal. We have to choose capital G in such a way. Okay, and not only that, you see, I was estimating this is in minus infinity to infinity. My goal is to obtain the lower bound, right? So what we are doing, that we start with this. So this is our middle term, what we want to estimate or to have the lower bound, and it was evaluated in, or the estimate or the L2 norm is taken from minus pi to pi. Okay, but I want this term dominate this integral, which is taken from minus infinity to plus infinity. So the obvious way to choose or to put a condition on small g is that g has support only inside minus pi to pi. Okay. And not only that, I want it is a positive function and it is bounded by 1 small g. Okay. When t is belongs to pi minus pi to pi. Okay, so this is one condition for small g is needed, and if we have that, then you see that above this inequality holds. Okay, so now next I was claiming that I pointed out here that capital G also we need as even function. That means that g phi is equal to g of minus phi. Not only that, I want g0 is strictly greater than 0. And whatever I was telling in the second term, this summation has to be less than strictly less than or less than some positive constant c naught, which is independent of k. Okay, it is uniform in k. And not only that, g0 is strictly greater than c naught. If we have all such properties, then we hope to get that lower bound as we required. Okay. So the choice is given in Ingham's paper, but there are plenty of other choice of such functions. Okay, but here I was taken whatever Ingham suggested. So here the small gt he took, that is cos t by 2, and when modulus t is less than equal to pi, and otherwise it is equal to 0. Okay, and then if we calculate that capital G phi, so you will get in particular, it is in this, it will have this form 4 cos pi phi by 1 minus 4 pi, phi square. Okay, and you can see that whatever that conditions we are just putting above, condition 1 and condition 2, at least that summation we will check later, I mean now, but otherwise other conditions for small g and capital G holds. Okay, so that's what you will get here. Okay, so now only one thing is remaining, that is that how to get or how to estimate this summation, okay, for each k. So this sum over n, so for each fixed k, suppose you were taking. Okay, so here we will have to precisely use that gap condition. So that condition will give us that modulus mu k minus mu n squared is greater than equal to that quantity if k is not equal to n. And don't forget to remember, so you have to remember that gamma 1 is strictly greater than 1. That is also given. Okay, so using these two, afterwards it is a straightforward calculation. Exploiting all these properties, ultimately you can bound this sum in some particular way. So at the end, what you will get here, that 4 by gamma 1 square is coming. Okay, so this line we used that gamma 1 is strictly greater than 1 at some point. So now it is equal to 4 by gamma 1 square. Now summation of this telescopic series is coming. And if you calculate, so this value will be given by 1. Okay, so it doesn't ruin anything. And then in particular, that whole things is equal to 4 by gamma 1 square. So whatever that C0 I was writing here, so I get it C0 equal to 4 by gamma 1 square. Okay. And also note that I want G0 also, right? So if you take P equal to 0, G0 is equal to 4. Okay, and here also gamma 1 is strictly greater than 1. So G0 is strictly greater than C0, that also holds. Okay. And so once we have this, so now it is everything straightforward. We just put that value, whatever that lower bound we get, C0, and from that inequality we ultimately get this inequality. And if we put all together, so we will get 4 into this 1 minus 1 by gamma 1. So we need basically gamma 1 is strictly greater than 1. And then that summation of that coefficients, okay, into sum of xk, that series is coming. Okay, so this is fine. So now if we want to go back our old file, that any interval that minus t to capital T, we that have to add or adjust that scaling factor. So if we do everything, so then ultimately we'll get that constant C1 looks like 4 pi by T into T square minus pi square by gamma square. Okay, so that gamma was that original gap condition what was given. Okay, so we'll come back to that coefficient little later once we prove that other inequality. So in particular, we prove that first inequality with that coefficient or that with that constant C1. Okay. So this is that particularly that left hand inequality, which was more important to us to study the inverse problem. Okay. So that suppose is okay. So now, yeah. So any questions so far? Okay. Okay, so I can go to the next part. Yeah. So next part also we will use the similar trick, but we will instead of minus pi to pi, the idea is that to use or do the change of variables such that we reduce the case where that L2 norm is taken from minus pi by 2 to pi by 2. Okay, and then if we calculate that gap condition of the new exponents, so then you will get it is equal to gamma 1, which now looks like 2 into t gamma by pi, which is strictly greater than 1. Okay, so again it is enough to prove the inequality for t equal to pi by 2 and gamma is strictly greater than 1. Okay, and why we are taking pi by 2 instead of pi? Because you see how we choose the gt will have the lower bound when t is only from minus pi by 2 to pi by 2. Okay, and that's what we will exploit here. So they are okay. So now we need the other inequality, right? So if we start from minus pi by 2 pi by 2, that interval, then it is anyway less than equal to, okay, so there is a typo, it is not h, it is g. Okay, because gt is or 1 is less than equal to root over 2 gt, that's what I am using, that left hand inequality. And here if we use that, okay, this is not ht, this is gt. So if we use that, okay, I think I did some typos here. So, okay, so if we do that, so now again, it is whatever we just calculate in the previous slide, again, it looks like it is from minus pi by 2, pi by 2. This is GT into that summation. And then again, we do the series expansion and etc. And here instead of, okay, this is again a typo. It is not capital K, it is capital G, as we just saw in the previous slide. Okay, so if we do that everything the same, exactly same way if we do, and we know that estimate also of that capital G at mu n minus mu k and the summation over n not equal to k. So that is also 4 by gamma 1 square, as we have just above. So if we use all these things, so here we will get just upper bound, which is straightforward, 8 into 1 plus 1 by gamma 1 square, and then that series of L2 little L2 series involving that xk, that coefficient is coming here. Okay, so that's what precisely our C2. Then again, if you adjust that scaling term, so that C2 looks like in this particular way, where gamma and capital T was given at the beginning inside in the statement of the theorem. So involving that those two parameters, you have that constant C2, and you in particular prove that right hand inequality with the constant C2. Okay, so that was the case when we proved the right hand side. Okay, but here I have one remark, I mean, which was already also studied. So if you see the proof of the right hand inequality, here you basically don't need that T gamma is strictly greater than pi. So in particular, that right hand inequality holds, that is basically related to the well-posedness of the PD also. So it, I mean, it is naturally it should happen for any T greater than 0. And this is the case that right hand inequality holds for any T greater than 0. Okay, so if you see in the previous proof, we only use that T gamma is greater than equal to pi by 2, and in that setup you have the result already. So now you consider the other case. In suppose T gamma is strictly less than pi by 2, that is the complement part, no? So if this is the case, then also you can do some change of variable, and again you bring it, you can estimate this L2 L2 norm of this term from minus T to capital T. Yeah, so this is again you do some change of variable, and then you go from minus T to capital T interval to minus T gamma to T gamma, and then what do you do? Yeah, so then okay, so now you know that your T gamma is strictly greater than pi by 2, and you are looking for the upper bound, so you dominate that integral by the same integral. Now it is from minus pi by 2 to pi by 2. Okay, and once you have that, this right hand side here, you know the estimate already by the previous step, because it is now the interval between is minus pi by 2 to pi by 2, and if you see the gap condition of the exponents, that is also satisfies strictly greater than equal to 1. That's what you had earlier. Okay, so now you use your previous result what you have already. Okay, so in conclusion, it doesn't matter that T gamma is strictly greater than pi or pi by 2. Okay, when you prove the right hand inequality, it is that right hand inequality holds for any T greater than 0. Okay, so but to just you should be careful that the left hand inequality, the first inequality, holds if capital T is strictly greater than pi by gamma. Okay, and if you note that coefficient C1, how we derived, so if you see that if T is goes to pi by gamma, then that C1 degenerates. Okay, C1 is going to 0. So it's unlikely that in general setup or all the cases, even you can reach T equal to pi by gamma case. However, this is the critical case when T is equal to pi by gamma, and so some cases you may get the inequality, the left hand inequality, but there are some example also where you don't get the inequality at T equal to pi by gamma. Okay, so the in conclusion, what I'm trying to tell, that the left hand inequality, to hold the you need that capital T is strictly greater than pi by gamma in general. Okay, and for the details and even that counter example, etc., you can see those reference they have constructed and discussed elaborately. Okay, so this is the part from Ingham, and now if you have any question you can ask on that, because now I will just give a brief idea how it comes when we are solving or we are studying the control problem, controllability for Navier-Stokes equation. Yeah, so if you have any question you can ask on this topic. Yeah.
Is the compactness important here? Can
uh,
one have for other orthogonal expansions this sort of inequalities?
you mean other which type
Like
of
R,
uh,
but there you may not have this sort of condition. So
yes,
yeah,
that
I'm viewing
gap
it
condition
in a
kind of
sense that
uh,
these omega k's are like not exactly perturbation, but it's some
yes,
other
kind of
sequence.
perturbation, yeah, I agree.
Yeah.
Yeah. Uh-huh.
So and then if on instead of this orthogonal system, which is of exponentials,
Uh-huh.
so can one get such sort of inequalities for some other kind of orthogonal expansion? There are
Okay,
other.
oh, that I don't know very well. Yeah, but even for exponential type of thing also, I think there are still some issues. I mean, this is very particular, no, I into omega k, and it's kind of perturbation from k,
Mhm.
right? Yeah, even yeah, I will show some result, but that's all involves the exponential. Yeah, what you are telling that It may not be in the exponential form, but some other orthogonal type of things.
Yeah, there are other functions, no? Like for example, there are polynomials,
Yeah. Yeah.
particular combinations of polynomials which can be orthogonal on this compact
Uh,
interval.
yeah. But I don't know if any direct such a type of inequality holds or not. Yeah. Is
Okay,
that there? I mean, I don't know. Is
I don't know. I mean, I'm just
I also
asking
don't know.
perhaps.
Yeah, but there are some. I think some. Yeah, still even for exponential case, even some other case. That's what I will show in maybe next few slides. Yeah, if that omega k is little bit different, or it is now it is purely real, and that's what I omega k is like purely complex or imaginary only. So suppose now it is mixed type, yeah, then also we don't have any, I don't know any particular, any good reference for that. Yeah, so for our case, somehow it could be manageable. Yeah, so I think that's also maybe open is my,
Okay, okay, thank you.
yeah, okay. Yeah, so yeah, so that is another things. Yeah, yeah, so that may be okay. So okay, so far we are talking about that exponential, that e to the power I omega kt form, where omega k is pure, I mean is real numbers. Okay, but even the case when now suppose the exponentials in the form of e to the power minus lambda kt, I mean, in particular, omega k is purely imaginary, say I into lambda k, and then the exponential looks like e to the power minus lambda kt. Okay, in this particular way. So that is also not in the I mean that this Ingham's inequality, whatever that assumption we just stated. I mean this case also doesn't fall in this on that particular pattern. Okay, so here also I think now we need a different type of inequality. So that is also studied very long back. I think this is due to Moon's Shah's theorem or inequality. So they are telling that now these lambda k's are real again, and it has a particular order. It is in increasing order. Okay, strictly increasing order, and it's a non-negative numbers. And not only that, that summation of 1 by lambda k is strictly infinity. So in particular, you can consider lambda k is equal to k square. Okay, and ultimately you get this summation 1 by k squared is finite. And so for such exponentials, do you have any inequality or not? Just to note, I think who are familiar, whatever we are discussing, no, earlier, so we started with wave equation. You saw that expansion of wave equation involves that e to the power kt, or in particular e to the power omega I omega kt. Okay, it's complex. But this case actually is typical for heat operator. Okay, if you see that Laplace operator, no? So that eigen one dimension, if you just think, it is like minus k square, the eigen values. And for heat, if you write down the expansion of the solution of the heat equation, then this e to the power minus lambda kt exponents will come. Okay, in the expansion. So now what we basically, this particular inequality we are looking for, that will help to study in our point of view the observation problem for the heat operator or heat equation. Okay, so that's what I just want to mention. And later I will call this is like parabolic type inequality, and the previous one is basically hyperbolic type, because it was related to wave equation. Okay, from PD point of view I'm talking about. So okay, so here, okay, I don't go to the detailed proof, but the main idea is that okay, so yeah, so I don't know, maybe what you were asking about this that that other type of that polynomial type of orthogonal set, no, or basis. So maybe this type of theorem can be extended. I'm not sure the exact reference. Okay, But here the main idea is that the theorem is like that if this summation of 1 by lambda k is equal to infinity, then we can tell the span of, here I wrote x to the power lambda k, but you can replace it by e to the power minus lambda k t. This span is basically dense in C01 if and only if summation of 1 by lambda k is equal to infinity. So in particular, if that summation of 1 by lambda k is strictly infinity, less than infinity, then this linear span of e to the power minus lambda k t is a proper subspace of L20T. And hence, you can show the existence of the biorthogonal sequence, okay, in the complement part of that L20T, and it satisfies some particular estimate, which will help you to prove this inequality in particular. Okay, that whatever that inequality I wrote here. Okay, so I mean, I am not going to the proof, but we need some generalized version. Yeah. So another one important thing which we needed. So that's a little bit generalization of the Ingham type inequality. So in particular, we need that or that type of inequality for the exponents when this lambda n. I mean, there are two things I mentioned. One is particularly in the form of I omega k, where omega k are real. Otherwise, it is like minus lambda k when lambda k's are real, and it satisfies some properties. Okay. But in our case, we'll see that in particular, we need the two set of exponents where lambda n is basically in the form of lambda nh, or I mean, it has, real part as well as the complex part. So the complex part is more or less like a wave equation, that IKT type of things, what we just saw. But you still have, some sense the perturbation, but perturbation by the real terms. Okay. Whereas even for the parabolic part also, what just Moon's theorem I referred, but they are also that lambda n's are purely real. But here we don't have, it is not real, it could be complex, but the real part is dominating and it is behaving like n square, and hence that 1 by summation, well, that summation of 1 by lambda n, that property will hold for the real part only, and imaginary part is going to infinity, but its order is less than by the real part. Is their order is like order n. Okay, so the real part will be dominating, and some sense we will be able to use those theorem in particular. Okay, so in our case, we will see that both type of exponents occur. Okay, and but we don't know or don't have any mixed type of inequality. Okay, that was the problem. Okay, so yeah, but this type of little perturbation when we have, so each separate case we can have, so this is a slight modification of Ingham's original argument, that when this lambda nh has this particular form, then still we can get the inequality. So this is simple, but the other one, so this is need some extra effort to prove, when this is a generalization of Moon's theorem, and here we have these exponents lambda in p that could be complex, and but we will have a correct some suitable modification now that exponential is coming with real part of lambda np, and this proof needs some detailed modification or some involvement, and that is due to Hansen. I think at the end I referred the paper, so we can see from that if you are interested. But suppose you believe that we have these two inequality. Okay, so then we go to this, okay, so let me just briefly tell what is that compressible equation, and then I will stop and we can see. Okay, so this is a Navier-Stokes equation I took, and that is basically linearized around a constant steady state, rho s and us. Okay, so they are constant, it's one dimension. So if we linearized, we will get a linear PD. Okay, so if you see the first equation looks like more, I mean, it's like transport equation, so it will have a hyperbolic behavior, and so we are, we can compare with wave equation in particular. Okay, the second one, if you see, this is more like heat equation. Okay, and that's what that parabolic exponent or parabolic inequality I was talking about. Okay, so now if we do study the well postness and etc., so I skip those parts. So idea is that you write this PD in a time dependent operator equation involving the linear operator A, whose domain is domain of A. Okay, domain of A, and then if we study the spectrum of that linear operator capital A, so then we see that capital A has two family of eigenvalues. Okay, one will be like lambda hn, just now I was explaining, so this will call hyperbolic type of exponents, and the another one is like parabolic type, so that is lambda np, whose real part, that is the dominating part, and that is behaving like n square. Okay, so these two family of eigenvalues we are getting, and but the good thing is that we can see that eigenvalues satisfy a uniform gap condition, and so we will exploit that. So okay, I skip the details, but the okay, you can see the diagram. So that blue colors is like hyperbolic type of eigenvalues whose real part is convergent to that minus omega naught, but the imaginary part is going to infinity. Whereas this red part points at the parabolic eigenvalues which are going to infinity, and the real part is behaving like n square, whereas the imaginary part is behaving like n. Okay, so now suppose we have this. Okay, so I just state the theorem and the connection with the Ingham. Okay, and then I will finish. So what we studied basically that the system is we call it null controllable at any time t, provided capital T is greater than 2 pi by us, and for any initial condition rho naught u naught coming from h1 dot per cross l2 using a control f which is acting inside the domain. Okay, so forget about that controllable, that null controllable, that term, because I didn't explain it. But the point is that it is equivalent to study the observation problem. Okay, so which kind of observability inequality? So in particular, we need to study the adjoint system and say sigma and v the solution of the adjoint problem, and whatever the theorem I wrote here, this is equivalent to study or to prove the inequality which is given here in particular. Okay, so that you can relate with the wave equation what I started with. So here v is the velocity, and we need to prove this inequality. Okay, and okay, and this is is bounded by that initial condition for sigma and v. Okay, so just to finish, so the conclusion is that you can write this velocity v in terms of that series expansion. Okay, using that exponents and eigenfunction and all these things you have to study and do. And then what do you get? That this b xt has this expression, but you see that now that exponents are coming in all together. So one is like hyperbolic type and one is like parabolic type, and I can't use either Ingham or Moonshaw's anything at all, I mean, in that combined form. So the idea is that, which is the tricky part, and maybe the novelty of that paper, that you decouple this V in terms of VH and VP. So that means that you decouple, or you have this type of inequality, which is not obvious, right? The other way was fine, but not this way. Okay, and suppose you can do that, then you can use this Ingham inequality for VH part, and that Moon's type of inequality for VP part. Okay, and hence ultimately you can prove the observability inequality. So that's how we managed to do in this particular case. Okay, So I will finish it here, but I will just summarize that in summary, that Parseval identity, we know it's very useful when we know that exponents or that basis functions, those are orthogonal, and it is helpful to study the direct problem and inverse problem both. But then the little bit generalization could be done by using Ingham type of inequality, and is very much used for inverse problems, okay, for PD. For the compressible case, we saw that we have both type of eigenvalues, and hence we get basically the mixed type of exponents. We didn't have any single inequality for that, so that was one serious blockage for that problem. But using the PD method, we are able to decouple and finally got the result. But it could be nice if we have a inequality for the both type of sequences, okay. And yeah, so these two also I summarize that for the wave type of PD, when you have the eigenvalues like In, then Ingham inequality is used, and that is mostly for the hyperbolic type of PD. Whereas the other case, like for heat equation, for example, when you have the eigenvalue like minus n square, then you use that Moon-Shor's type of theorem. Okay, so mostly for parabolic type of PDs. Okay, we use that. And okay, so then the some references. Yeah, so this is the first reference, I think here. Yeah, but they also talk about the families of exponentials, but they have some detailed study of such type of inequalities, and even that optimal estimate of the constant also. Okay, the first one. Okay, then this Hansen, yeah, he proved this generalized type of Moon-Shor's inequality when that exponents are still complex. Okay, and the Ingham, that was the original paper. And for non-harmonic Fourier series, there are some interesting result and useful theorems we can see from this reference by Young. Okay, so that's what I planned. So I finish it here. Thank you.
Okay, thank you for a really nice talk. Are there any questions? So yeah, I had that question which I asked you earlier about, and then in the when you said the decoupling inequality.
Yeah.
So if you could explain that a bit, maybe.
Oh yeah, okay. So is the PD level we did in particular, huh? Because here, no, the other way it is fine. You can use triangle inequality, right? Norm of L2 norm of V is less than equal to L2 norm of VH plus VP is fine, no?
Yeah.
But the other way we don't have. In general, right? So here we basically used, that is kind of PD property that it's a transport equation, no? And that coupling, if we see, that it was zeroth order and first order coupling in the equation. So what we did basically, that VP mostly coming from that parabolic part. That's the heat equation, and we ultimately show that if T is very small, 0 to T pi, say T epsilon or something, then that hyperbolic part can be dominated by the parabolic part. So we had some inequality in the PD level, and that somehow we used there to decouple, or like solving the parabolic part first and then putting that parabolic part inside the rest of the PD and solve the hyperbolic part in some sense.
Mm-hmm. Okay, and this constant, what is it dependent on? That C, that in that inequality, the reverse.
Here, no? Oh, so that will depend on capital T and this O, and even that gap condition, no? Gamma or something.
Mm-hmm. Okay. Okay, yeah. Thank you.
Okay. Thank you. Yeah.
Yeah, so are there any more questions? So if not, let's thank the speaker for a really nice talk.